We currently have stowed the absolute greatest dark openings at any point kept in the set of experiences of science that have eaten up more than 20 billion stars. We physicists have paused a long time, beginning around 1916, for this photo. In excess of 20 billion stars have been gobbled up by probably the biggest dark openings at any point found in logical history. Few mysteries in the tremendous universe have charmed the interest of stargazers and astrophysicists, however much dark openings. Cosmologists utilizing the James Webb Space Telescope have uncovered a critical disclosure that will change how we might interpret the size and extent of dark openings, and a dark opening gauging maybe 2 to multiple times the mass of the Sun. How much do we currently have some familiarity with these odd voids, and what did they find? Show up with us as we set out on an undertaking all through space. These dark openings were found half a month prior, and their mass leads us to presume that they are really quasar extras. How about we begin with an outline of dark openings prior to digging into the revelations made conceivable by James Webb's cutting-edge hardware and logical undertakings? A lot of matter is brought naturally into a very compact space by dark openings, which are infinite elements noted for serious areas of strength for their gravitational attraction. This peculiarity is at times alluded to as a gravity well on the grounds that even light can't get away from the gravitational draw of dark openings. They appear as dismal voids in the texture of the universe. More modest dark openings are scattered across the universe and are normally created as the remnants of enormous dying stars. Interestingly, the focal point of almost all gigantic universes is dominated by truly massive dark openings with cosmic masses between 1 million and 1 billion times that of the Sun. The origins of very large dark openings are still unclear. Following quite a while of study, understanding how these entities form and achieve their astonishing masses remains a challenge for experts. Researchers are captivated by these giants that govern the centers of galaxies throughout the universe, but they can't determine the process that led to their development. The latest findings reveal more of the truth, gradually exposing these mysteries to humanity. Earth is truly whirling around a dark opening in Sagittarius that is 2 to multiple times the mass of our Sun. Researchers are thrilled to have found a massive dark opening with a mass around 9 million times that of the Sun. This astounding discovery was made possible by the cutting-edge James Webb Space Telescope, which found this enormous object settled at a galaxy's core just 570 million years after the Big Bang. Beyond its apparent grandeur, this discovery is significant because it offers new insights into the origins of these cosmic giants. Researchers believe that further findings of this nature will soon emerge, helping to solve the mystery of the early appearance of these gigantic entities in cosmic history. Over the years, several discoveries have been made about very large dark openings and stellar mass dark openings, which are the 2 types of dark openings identified by researchers. Massive stars are thought to undergo catastrophic deaths that give birth to stellar mass dark openings, with masses typically between 5 and multiple times that of the Sun. These stars experience a gravitational collapse that culminates in a supernova explosion when their nuclear fuel depletes. A stellar mass dark opening, a gravitational artifact marking the death of a once massive star, is all that remains afterward. On a larger scale, the majority of massive galaxies, if not all, have extremely large dark openings at their centers. These vast cosmic beasts, with masses between 1 million and 1 billion times that of the Sun, remain beyond our current understanding due to their colossal size and powerful gravitational attraction. Their presence is evidence of the forces that shape the universe. However, their origins continue to fascinate scientists and provoke ongoing investigation. Unusual findings by astronomers suggest that very large dark openings are thought to form by persistently consuming matter until they reach colossal sizes. However, it is not so simple. These enormous dark openings, with masses exceeding 1 billion times that of the Sun and existing less than 1 billion years after the Big Bang, have been discovered by astronomers like Stephen Finlin of the University of Texas in Austin. How they could grow so large in such a brief period is astonishing. Researchers are examining the distant past of the universe, approximately 13.7 billion years ago, in an attempt to resolve this puzzle. However, it is not easy. Dust can obscure the light from so far back, making the early dark openings incredibly faint and challenging to study. It's like trying to solve a mystery with only parts of the puzzle. Perhaps the excitement of astronomy lies in its ability to explore an unknown area and gradually reveal secrets. Burns 1019, a recently found dark opening named Synges 1019, is concealed in a distant galaxy. This interesting finding was made as a component of the Inestimable Development Early Delivery Science Review, which completely analyzed worlds. The objective of this task is to approve the exploration strategies, notwithstanding testing them arranged in the recognizable constellations of Boötes and Ursa Major. The information obtained from the review has generated a great deal of excitement among the cosmology community. The data procured by JST's sharp eye could reveal previously unknown aspects of cosmic evolution. These revelations shed light on mass, chemical composition, and other significant characteristics that make this particular system unique. Through this examination, scientists can change how we perceive celestial processes and learn about the origins of the universe. Notably, they found 2 additional ancient, very massive black holes, so this discovery is not unique. Astronomers have significantly advanced their understanding due to this comprehensive study. They have made recent discoveries of black holes in galaxies like SE 1019 by combining extensive spectral data with near and mid-infrared images from the satellite telescope. Thanks to the telescope's exceptional capabilities, astronomy research is moving from theoretical to quantifiable insights. We can now view and study these phenomena in extraordinary detail due to its robust technology. As light travels from distant galaxies to Earth, it gradually becomes distorted, stretches into longer wavelengths, and shifts toward the infrared region of the spectrum. By searching for bright galactic nuclei or active galactic cores, thought to be the main indicators of black holes that voraciously consume matter and release enormous energy, insightful astronomers detected the black hole found in SE 1019. Researchers had long believed that early black holes were rare. However, they were stunned to discover that a vast number of active black holes from the universe's first billion years could be found in JWST's first observations. Equipped with highly sensitive infrared equipment on board, the SE review has proven immensely valuable. The distinctive nature of these black holes, in addition to being incredibly luminous, includes SE 1019, which is notable for its age and a mass of around 10 million solar masses. According to a fascinating NASA press release, this intriguing black hole is considerably smaller than the massive black holes observed farther away by other observatories, which possess masses exceeding 1 billion times that of the Sun. For context, let's look at the black hole known as Sagittarius A*, located at the center of our own Milky Way galaxy. It has a mass close to 4.3 million times that of our Sun. Though this seems enormous, it is relatively lightweight compared to modern supermassive black holes. The new discovery isn't as bright as previously found black holes, but the study also uncovered 2 additional cosmic lightweights, supermassive black holes with masses less than average for such distant objects. In addition to the core black hole within SE 1019, these objects were formed around 1.1 billion and 1 billion years after the Big Bang, respectively, and are located at the centers of galaxies SE 2782 and SE 746, each about 10 million solar masses. These black holes drive the cosmic output of their galaxies. Meanwhile, the presence of a cosmic heavyweight, like the 6.5 billion solar mass object at the center of galaxy M87, stands in contrast to these discoveries. The James Webb Telescope's view of the black hole in SE 2782 was unobstructed by dust, making it easy to spot. By contrast, the black hole in SE 746 presented some challenges, being partially obscured by dust from its bright accretion disk, suggesting it may reside in a star-forming galaxy. The findings from the SE review introduced us to a range of black holes, expanding our understanding of these colossal wonders and increasing their mystery and appeal. Researchers also made an exciting discovery at the center of their observations. They observed signs of a supermassive black hole, evidenced by rapidly moving plasma. Although this signal was subtle, thorough simulations and analyses provided a confident 95% certainty of this remarkable feature. The team is enthusiastic about future possibilities and anticipates even more important discoveries with upcoming observations. The significance of this signal will only grow as advancements in science and technology offer new perspectives on black holes and their surroundings. This discovery holds substantial implications, as SE 1019 appeared shortly after the Big Bang. Intriguing ideas about origins emerge from this surprising finding, confirming a long-held scientific hypothesis that supermassive black holes in the early universe arose through the merging of smaller components. However, there's an issue. The black hole in SE 1019 is massive. Two possible scenarios could explain its origin. The first suggests that SE 1019 may have formed even before galaxies took shape, directly from the collapse of a massive gas cloud, ranging from 10,000 to 1 million times the Sun's mass. Alternatively, it could have originated from the remnants of a supernova explosion from a star far larger than any existing today, up to 100 times the Sun's mass. Under such conditions, the black hole would have grown faster than current theoretical limits on black hole formation. If the first scenario is correct, it provides valuable new information about the period before galaxies formed. If the second scenario holds, it would mean we still have much to learn about the explosive growth of black holes. Finding low-mass black holes from the early universe is essential for testing these scenarios. Thus, the discoveries of SE 746 and SE 2782 hold great significance in unraveling the mysteries surrounding the origin of these cosmic giants and the history of the universe, the ultimate goal in astronomy. Although finding the holy grail of astronomy is thrilling, the journey to understanding it has only just begun. It likewise revives a well-established contention in the physics world. Envision going inside a black hole. What insider facts are ready to be uncovered? Would somebody who wandered into its grip aimlessly end up in the grasp of its massive gravity, or might they be sent off into obscure territory, an alternate dimension, or perhaps another period of time? Translating this complex inquiry explores one of the most curious areas of contemporary physics. Researchers study ideas like wormholes, white holes, and even the possibility of time travel, navigating a minefield of potentially hazardous theories. They consider higher dimensions, including the 11th dimension, with ever greater repercussions due to their mission. By identifying 11 distant galaxies that existed 13 billion years ago, researchers made an amazing discovery. These results were unexpected, as scientists had anticipated finding fewer galaxies at such distances, conflicting with earlier predictions. These new galaxies, featuring several rapidly forming stars, provide significant new information about the historical evolution of galaxies, thanks to the James Webb Telescope. The comparison with recently discovered faint light sources and the earlier, extremely massive black holes discovered in previous studies is equally intriguing. The latter were found within newly observed galaxies, while the former outshone their host galaxies. This odd brilliance inversion has fascinating implications. It implies that while larger counterparts grow to become increasingly brilliant, smaller black holes appear fainter than their host galaxies. This theory suggests that host galaxies grow more slowly than black holes, opening up new avenues for research and helping us understand the evolutionary history of these objects. The quest for ancient black holes has long been underway. The black hole of the quasar PSO J1019+26 is fascinating, yet there are also minor hints suggesting the possibility of even earlier black holes. A team believes it has observed an active galactic nucleus in the galaxy UHC-1, thought to have formed around 450 million years after the Big Bang. Meanwhile, the galaxy GN-Z11 may contain another active galactic nucleus, recently identified by the JWST Advanced Deep Extragalactic Survey, JADES. These findings offer new opportunities for investigation, representing a pivotal moment in our understanding of black holes and the early universe. We become more aware of the intricate and fascinating processes governing our cosmos as we work to solve the mysteries surrounding these massive phenomena dating back 430 million years following the Big Bang. JADES collaborator Kevin Hainline, an astronomer at the University of Arizona in Tucson, predicts these records will soon be broken. He believes we are entering an exciting era of galactic discovery and have only just begun to scratch the surface of a plentiful array of actively growing supermassive black holes in the early universe. Black hole insights from Michio Kaku. But first, a little detour. What does the eminent theoretical physicist Michio Kaku have to say about black holes? A black hole is, generally, a large, extinguished star with a gravitational pull so immense that light cannot escape it. NASA focused on the tiny core of M87, a massive cosmic engine located a staggering 50 million light-years from Earth. Though invisible, scientists found that the core of M87 was a turbulent vortex of searing hot hydrogen gas, spiraling at a speed of 1.2 million miles per hour. There had to be a massive object in the core of this maelstrom to resist its tendency to disperse in all directions. A black hole was created when this mass approached that of 2 to 3 billion suns, an unimaginable amount capable of containing light. The black hole rotates, but this discovery raises new questions regarding black holes. Using Einstein's gravitational equations, mathematician Roy Kerr of New Zealand described a rotating black hole back in 1963. However, there's a twist to Kerr's solution. It suggests that, in a parallel universe, a passage known as the Einstein-Rosen bridge could lead to an exit via a white hole. If someone were to fall into a black hole, to their surprise, they might not hit the ground as expected. Instead, they might emerge from the opposite side of the Einstein-Rosen bridge unscathed, possibly into a parallel universe. The fascinating notion of a wormhole presents the possibility of connecting two parallel universes or even remote regions within one. To picture this phenomenon, imagine Alice's Looking Glass, a famous portal to an alternate reality where logic takes strange detours. This is the analogy Kaku uses to explain how crossing the edge of the event horizon could swiftly transport one to a place reminiscent of Wonderland, where animals speak in riddles, and common sense transforms into surprising forms. Think of the event horizon as a doorway. Passing through it could take one to the opposite side of the universe or perhaps to a different time, when space and time merge. This vision appears as the merging of two universes linked by an ethereal mirror. With these ideas, the physicist opens us to new possibilities and invites us to explore the mysteries woven into the very fabric of existence. The wormhole and quantum theory. This is a concept physicists find extremely interesting, as the use of black holes, or wormholes, as shortcuts for time travel or for traveling between different parts of our universe is captivating and unique. However, doubt persists regarding this hypothesis. Critics point out that, given the reliability of wormhole solutions derived from Einstein's equations, it would be premature to dismiss them. The potential instability of wormholes, along with the presence of intense radiation and subatomic forces surrounding their entrances, poses a major deterrent for anyone daring to embark on such a journey. Critics acknowledge that many wormhole solutions are valid, yet there is an ongoing debate within the scientific community. Without substantial evidence, there can be no right or wrong answer. The issue is that Einstein's equations break down near the centers of black holes and wormholes. This inconsistency underscores a significant gap. While relativity explains gravity, quantum mechanics, which explains radiation and subatomic particles, is beyond Einstein's theory. Solving this discrepancy requires a unified theory that seamlessly integrates quantum theory with the physical universe. Both aspects need attention in a theoretical framework to fully understand the complexities of quantum black holes. This quest, sometimes called the theory of everything, may hold the answer to this enigma. Michio Kaku and the all-encompassing theory offer a vision of to consolidate the central laws of material science into two significant systems is a prominent achievement of 20th century science. The first of them is, in all honesty, Einstein's theory of gravity, which explains the origins of the Big Bang, as well as other massive objects like galaxies and black holes. The second foundation is quantum theory, which stands in sharp contrast. This structure reveals the world of radiation and subatomic particles, providing a microscopic perspective that unveils the universe's fundamental structure. Interestingly, there is some irony in this, even the greatest. Physicists, such as Einstein and Heisenberg, have struggled to reconcile these incongruous structures. The problem is that the two theories describe the universe in their specific domains, the vast and the tiny, using disparate mathematical equations and physical laws. Is superstring theory, then, a viable speculation? Superstring theory, a viable alternative developed by Michio Kaku, integrates gravity into a radiation theory necessary for interpreting the quantum wormhole code in a smooth and elegant way. A revolutionary discovery at the core of superstring theory is that subatomic particles, the fundamental units of the universe, are actually resonances or vibrational modes of tiny strings. These superstring vibrations correspond to the multitude of particles present in nature, much like the notes produced by the vibrations of a violin string. According to this theory, the universe is composed of these vibrating strings that together create the symphony of life. Remarkably, this symphony extends beyond sound to the curvature of spacetime. Superstrings warp the very fabric of space as they move through time, creating astonishing solutions to Einstein's equations, which include wormholes and black holes. Superstring theory unifies Einstein's theory and the quantum world into a single, powerful structure, a monumental achievement. However, it's not without its challenges, such as the complexity of higher dimensions. Here's where an unusual issue arises. Superstrings vibrate in a peculiar way. They only vibrate in 10 dimensions. This quirk is essential for its ability to integrate the forces governing our universe. Within these 10 dimensions, there is enough space to accommodate both the complex domain of subatomic physics and Einstein's theory of gravitation. Previous attempts to unify these forces encountered obstacles due to the limitations of the traditional four-dimensional framework. Fundamentally, this structure proved too small to include all the forces in a harmonious and coherent mathematical framework. We might imagine higher dimensions in the way Michio Kaku illustrated in a tranquil Japanese tea garden with a few carp lazily swimming along the lake's bed. The universe the fish live in is restricted to 2 dimensions, width and length, with no concept of height. The idea of up is endless, and the 3rd dimension remains completely alien. Now, let's add some raindrops to the lake to create ripples by gently tapping the surface. The fish can no longer see the 3rd dimension, although it clearly exists when they see waves rippling across the surface. Putting all of this to use in our everyday lives, we might infer the existence of higher dimensions even though we can't see them directly because of the ripple effects they produce. The universe and superstring theory vibrations crossing the 5th dimension reveal the very essence of light. Within this fascinating structure, a consolidation occurs as we embrace these additional dimensions. Today, scientists can account for a greater number of forces, including nuclear forces. Ultimately, all of this boils down to one simple yet fascinating truth: the more dimensions we include, the more forces there are. Why isn't this framework widely adopted if it seems so promising? Many scientists frequently question why superstring theory hasn't been proven. It primarily has to do with the fact that these higher dimensions are still inaccessible in laboratory conditions. As it stands, 4 parameters, length, width, depth, and time, can capture all events in the universe, from the tiniest subatomic decay to the magnificent display of galaxies, not 10. But the magic of 4 dimensions and the Big Bang remains compelling. According to some physicists, the universe was a fully realized 10-dimensional state at the time of the Big Bang. From this point, the universe thrived in the embrace of all 10 dimensions right from the moment of creation. Shortly after this explosion, an extraordinary thing happened. 6 of those 10 dimensions curled up, forming an incredibly tiny pattern that prevented them from being seen directly. This theory takes on the form of a creation story, explaining the universe's origins as a manifestation of 10-dimensional space's full potential. Unsurprisingly, the 10-dimensional superstring's math is both astonishing and incredibly complex, inspiring some truly spectacular work in this field. This theory has created entirely new areas of study and avenues for further research within quantum black hole investigations. However, there is still a small problem. Until now, no one has been able to solve the mystery of a quantum black hole. As we enter the 21st century, as Edward Witten of the Princeton Institute for Advanced Study amusingly put it, string theory is 21st century physics that accidentally fell into the 20th century. Indeed, the science needed to solve quantum black holes may soon be discovered. Despite the tremendous stakes, dedicated groups of physicists are venturing into the maze of superstring theory. Progress is being made slowly, yet steadily, and there is still hope. Separate groups of physicists independently discovered something astonishing that sent shockwaves through the scientific community. String theory holds the key to unlocking the mystery of the quantum black hole. There's a catch, though. Due to their complexity, the calculations must be done in 2 dimensions, not all 10. In summary, it's still a significant breakthrough, and many physicists are beginning to look more optimistically at the situation, believing that it will only take time for a brilliant mind to fully solve this complex puzzle. Until the remarkable work of telescopes like JWST, we were unaware of the true size and timing of black holes. Although smaller black holes were thought to have formed in the early universe for some time, scientists had never observed them in such intricate detail until these recent discoveries. Although the possibility of these lower-mass black holes existing in the early universe has long been recognized by scientists, the Webb telescope is the first observatory capable of observing them with such clarity. The potential that these lower-mass black holes are truly scattered across the universe, simply waiting to be discovered, is made possible by these new revelations. The careful examination of JWST CHAR's data reveals a lot. 11 galaxies have been identified, and their existence dates from about 470 to 675 million years following the Big Bang. This discovery has far-reaching implications, extending beyond observing these celestial bodies. Rather, it opens the door to a completely new era of astronomical exploration. The data obtained from the in-depth study of these 11 galaxies may provide the foundation for future research into the origin, evolution, and ultimate development of stars, galaxies, and black holes. These discoveries allow us to look into the distant past, reconsider the present, and even potentially predict the future course of celestial objects. The remarkable capabilities of the James Webb Space Telescope promise an abundance of data for universe exploration. This discovery challenges preconceived notions, creating new research directions and significantly reshaping our understanding of cosmic events. With every astounding finding and image it generates, James Webb continues to be a beacon of hope for scientists, solving long-standing mysteries and bringing us one step closer to unraveling the profound secrets of the universe.